y is equal to r sine theta. We had a really complicated conversion for z. What was the conversion for z?
Z0.
It's
Z.
equal to itself, right? It's just equal to itself. And then one other thing we need to keep in mind, the one little cheating thing we have, is that x squared plus y squared equals r squared. So this is also a helpful fact to know. And what we ended with talking about last time were some really cool shapes or solids in 3 space that we can create using cylindrical coordinates. And so some of the ones we had talked about really quickly is if r was equal to some constant c, then what we ended up getting was a cylinder. Because theta can be a free variable, we can rotate all the way around with that radius, and z is free, so we get all of the elevation. We'd also talked about what if theta was a constant value. And if theta is a constant value, that means we have a constant angle, but we can go any height we want and out as far as we want, which means we ended up with a plane. And finally, we had said if z is a constant. And if z is a constant, what happens? We have constant elevation, right? But everything else can vary, so I get a plane, right? Because I have a constant elevation, I can go as far out as I want for r and all the way around for theta, so I get a plane for this as well. Now, I think the one you guys are thinking about here is, well, what if z is equal to r? And that was what? Cone, right? Because I said the height is directly proportional to my radius. It means the higher I go, the wider I get from my radius. And so what happens is at 0, I have nothing, and then I gradually spread out, so I'm in a circle all the way around, and so I get a cone.
How do you get a sphere?
How do you get a sphere? We're going to actually talk about the fact that cylindrical coordinates are really nice for cylinders. They're really nice for cylinders because all I have to do is set the radius constant. In fact, generating a sphere in cylindrical coordinates is not as easy as it might sound, which means since spheres are very, 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 very common, we might want a whole new set of coordinates, later what we're going to get to today, that's easy to generate spheres on. So, cylindrical coordinates are really good for cylinders. Hopefully we'll get to spherical coordinates today, which are going to be really awesome for generating spheres. That being said, what we really want to do here is learn how to do triple integrals. In cylindrical coordinates. And so what we're going to talk about here is if we want to integrate some function over a 3-dimensional solid E. And so we bound E up. We say E is bound by x, y, z, such that x and y is in some domain z. And z is bounded by 2 different things. We write those 2 different things because we want to be able to write them not just as numbers, not as scalar values, but as functions. As u1 of xy less than or equal to z. Oops, says z, I wrote that. Less than or equal to u2 of xy. And I said we were doing cylindrical coordinates, right? And so this doesn't look all that helpful for cylindrical coordinates. What we're going to do is define where x and y are bounded. That is how they're bounded up in D. And we're going to define the domain to be in polar coordinates. We bound R between, what letters did we use? I think we've probably used A and B. Sounds right. I'd like to be consistent, but I actually can't remember back when we did polar coordinates a while ago. And I found alpha and beta for beta. And so essentially what we're saying here is we want to do cylindrical coordinates really if and only if we end up with this domain in 2 space that has good polar conversion. That is, we want to do cylindrical coordinates if when we take that slice, that cross section, if we get a circle or a disk. So before we write anything down, when D is a disk or circle. As if when we draw that cross section, we end up getting a circle out. That's really what we want to run with on this. When we set up an integral, we'll call it triple integral here, over E of some function f, x, y, z, dv, as we're integrating our function coordinates, it ends up being split just like if we had originally gone back and looked at polar coordinates for our outside. If we're looking at polar coordinates, what integral always goes on that side? Theta or r? Theta is always going to go on that side, right? So my first integral is going to be bounded between alpha and beta. The next one will be bounded between a and b for r, right? And then finally, I want to write this as u1 and u2. My problem is, though, that when I swap these over, I'm not going to have an x and a y in there anymore, right? Because I've swapped my x and my y into the polar conversion in 2 space. Which means, rather than write this as u2 of xy, it'll be u2 of what? R cosine theta. R sine theta, right? And u1 will be R cosine theta, R sine theta. We can also write these as functions of R and theta if we want instead, to make it nicer looking. Okay, the big question is what goes on the inside? Well, if my function was originally of x, y, and z, f will be of R cosine theta, R sine theta, z, right? Perfect. Now there's one small little thing, and that is when I convert normally into polar coordinates for my 2 integrals, what do I normally put on the end? What goes here? R. Conversion is exactly the same as if I were to go first with z and then into polar coordinates. Cylindrical coordinates just allows me to convert over right away. So I'm going to put my r there, and when I run this, I'll run dz, dr, d theta. Kind of a monster, right? It's a little bit long. Now, there's one thing we could change about this, and that is when we talked about polar coordinates a while ago, we said that r doesn't always have to be bound by scalars, right? It doesn't have to always be bound by constants. We did the one example where we had a cylinder coming up, it hit the paraboloid, right? And we had this kind of funky shape going on. The problem with it was that when we looked at our d, it wasn't centered at 0, right? It was centered at 0, 1 instead, or 1, 0. Remember what I'm talking about? We had that one that was centered at 1, 0 instead of 0, 0. In that case, r wasn't bounded between 2 numbers, but rather by 2 functions. So the only thing we could change about this here is that rather than bound r between a and b, I could bound it between h1 of theta and h2 of theta. And all that would change is over here, I'd run it from h1 of theta to h2 of theta. So then I could bound r by a function instead of by actually 2 constant values. Now it's kind of weird to look at it like this, that is kind of abstractly, so what we really want to do is look at an actual example. I'm going to erase all this and we'll put one up here. The steps to evaluate things in cylindrical coordinates are still going to be exactly the same. The first thing we're going to do is draw it. Then we'll draw the cross section, make sure we want to do cylindrical coordinates. We'll convert and find our bound. We'll set it up and evaluate. So, let's look at an example here. A solid E. Lies within x squared plus y squared equals 1. How do I know right now that I want to do cylindrical coordinates? It's a circle, right? As soon as I see that, I'm thinking polar for 2 dimensions. We'll get solid. Definitely want to do cylindrical. Below z equals 4. And above z equals 1 minus x squared minus y squared. What bounds am I already given? Which variable am I already having bounded? Z, right? Because I have 2 functions in z here. Here I have z equals some function of x and y. Here z equals a constant function, right? So I can see bounds for z already. Despite that, I still want us to work on our visualizing, so we're going to sketch out the solid first. Okay. I am bound within x squared plus y squared equals 1, right? X squared plus y squared equals 1 is a circle in 2 space what does it create in 3 dimensions? Cylinder, right? Because I have a circle and then any z value I want. So right away I know I have kind of a circle, right? I'm going to go ahead and sketch it out really quick. What's the radius of that circle? Radius of 1, right? So I'm thinking I have a cylinder. A radius 1. The only problem here is I've got 2 bounds for z. I know I'm bound below 4, so I'm going to go ahead and put a mark up here at 4. Right? And I'm bound below by a function. 1 minus x squared minus y squared. What kind of shape is that? To figure it out, we can cover things up and look at traces. That's definitely a parabola, right? If I cover up x, everyone's okay with that? Is it facing down or up? Down. What is the vertex of that parabola? Where is it maxed out at? 1 for z, right? Because it's 1 minus something. So the biggest it's going to get is 1. So I've got a parabola that's maxed out at 1. Okay? If I cover up y, that's a parabola. Same idea, right? It's maxed out at 1. Which means if I sketch this out, I have a parabola. It looks like this, right? That is my lower bound. 4 is my upper bound. And it's all contained within a cylinder, right, of radius 1. Which means what's happening here is I have the cylinder, which apparently has very curvy sides. Goes down, hits this, and on top, I'll even make it look a little bit more like a cylinder. There we go. A cylinder can't be in the xy plane. A circle is in the xy plane. A cylinder is 3 dimensions, so it has to be elevated as well. This is a circle. It doesn't specify z, so z can be any value I don't want it to be. I want you to think about what this looks like. I've got a cylinder, right? And it's got kind of like a dome at the bottom of it. Actually, couldn't have been more perfect. Essentially what I have is the shape of the water bottle, right? And on the bottom, I have kind of an inset. Kind of like a little mound that's cut out. In fact, exactly like this water bottle. It's got a little bit of a dome on the inside cut out of it. So what we want to do here is we want to actually find the volume within this. That's a really terrible drawing. It looks really good when I'm standing really close to it. Like I'm like here, I'm like, oh, I'm perfect. And I step away and it's awful. Okay. So cross sections. Where do I want to place this with? Don't overthink it. Which one do I already know? Which one do I already have bounds for? Z. So we're going to cut across Z. Done. When I cut it across Z, XY plane, what am I going to have? What shape am I going to get when I take this cross section and lay it down? Circle, right? Go ahead and draw a circle. And that right there says do cylindrical coordinates. As soon as I see that, I know. I also know from here, which consequently is what gives me this shape, right? As soon as I see these two, as soon as I know I want to work with it, the next thing I need to do is find my bounds. Let's talk about Z first. I know I want to bound Z under 4, right? Because I run from the top here down, and it's not always going to hit 0, right? It's going to stop where I hit that little dome that's bounding it below. What is the equation of that dome? 1 minus x squared minus y squared, right? There's a little bit of a problem here, and that is, if I want to do this in cylindrical coordinates, there's no x squared and y squared, right? What can I do with this to make it nice? I can factor out a negative, right? Exactly right, guys. And what is x squared plus y squared? R squared. And so I've found my bounds with the functions originally given and converted them over to cylindrical coordinates. Now the problem you guys ran into with your homework is that this wasn't a square and that wasn't a square, right? If you had had 8 plus x squared plus y squared, your life would have been infinitely easier. As soon as I walked out of the room, that evaluate for 0.